Hi children, welcome to another chemistry session. Today we are going to discuss one of the very important chapter from the 12th standard topic, coordination chemistry, complex chemistry, right? Very important chapter. One or two questions generally come for the exam. All competitive exam when you take without a question from this chapter, you can't find a paper. A very important segment. Okay, let's go through the coordination chemistry and the important aspects dealt in the chapter. All of you know coordination compounds are formed by the complex compounds are formed by transition elements. Mainly transition elements are forming coordination compounds, right? Many elements can give, but still most of the complex compounds are generally formed by transition elements. And what are the various coordination compounds, and what are the different aspects of understanding complex molecules, and what are the important theories, how the naming can be done, what are the kind of isomerism dealt in the chapter, everything we are going to discuss in the video. Okay, can we go through? Yes. See, when you simply analyze the introduction portion of the chapter, you can find the importance of coordination compounds, which is called complex compounds. Modern terminology is coordination compounds. Complex compounds, mainly given by transition metals. Transition metals are giving coordination compounds, which is called complex compounds, right? See, the metal atoms are bound to a number of anion or neutral molecules. A metal atom will be surrounded by a number of anions or neutral molecules. Many of you know, but still we can understand. If we take, say, for example, cuprammonium complex CuNH3 4 times SO4. See, the neutral molecules are surrounding the central metal atom copper, right? It can be anions surrounding. It can be anions surrounding. You see that CO, H2O, 4 times Cl2, Cl. Look at the complex. It can be neutral molecules or it can be anions. Water molecule is a neutral molecule which acts as a ligand surrounding the central atom. Hope you remember the term ligand. Ligand means ligaire, an atom or group of atom connected to the central metal atom. So central metal atom, normally a transition metal which is bonded to neutral molecules or anions most commonly. Of course, rare occasions it can turn some cationic species also involved in complex formation, but usually electron-rich species, neutral molecules or anions are involved in the complex formation, while the modern terminology is coordination compounds. All of you know why it is called coordination compounds. There is a dative bond formed between the central metal atom and the ligand. If you take cuprammonium complex, copper is bound with ammonia, forming a dative bond using the lone pair of electrons of nitrogen atom, right? So it is quite simple to understand the technology, technique involved or the technical term involved in the particular area. The ligands can be understood as, yes, Lewis bases. Ligands can be understood as Lewis bases, where the central atom will act as Lewis acid. Central atom act as a electron pair acceptor, and the ligand act as electron pair donor. Electron pair donors, all of you know, it is acting as Lewis bases, and the central atom will act as Lewis acids, right? So a central metal atom bound to a number of anions or neutral molecules, and thereby we get a complex molecule. Complex molecules are basically formed by the combination of simple and stable molecules. Simple and stable molecules combining, you get complex molecules, which are called coordination compounds. Imagine you take simple molecules like copper sulfate which is colorless in nature, when interacting with water, it turn blue in color due to pentahydrate formation. It turned blue in color due to pentahydrate formation. Right? Copper sulfate, which is colorless, turned blue when treated with the moisture content, when treated with water. It formed blue vitriol. Blue vitriol. What is the actual representation of that molecule? Many of you may be remembering, it is Cu H2O 4 times SO4 dot H2O. Out of 5 water molecules, 4 water molecules are forming a coordinate bond with the central copper, and 1 water molecule is hydrogen bonded with the sulfate, forming hydrate structure. Right? And now subsequently, when the solution of copper sulfate, this can turn copper sulfate aqueous solution, which again is blue in color. Imagine this is treated with ammonia. You will get a deep blue colored complex. Deep blue colored complex. That is cuprammonium sulfate. This is called cuprammonium sulfate, which is deep blue in color. And you can very well understand the water molecules are replaced by ammonia molecules. Now there is a change in color and you get another different complex. My point of discussion is simple and stable molecules get converted to complex molecules by chemical reaction. Right? Take another example. Where you can find a simple compound, say KCN, interact with another simple compound, ferrous cyanide, and you are getting the complex K4FeCN 6 times. This is a simple stable compound. So two simple salt forming a complex salt. So how the complex compounds are formed? Complex compounds are formed by the combination of simple and stable molecules. Is it clear? How much importance these molecules are? They are industrially important. In the laboratory reactions, it is important. Commercially, it is important. Biological segment, complex molecules are very, very important. When we are talking about vitamin B12, it is so-called cyanocobalamin, vitamin B12. Cyanocobalamin. It is a cobalt complex. Very simply, when we talk about chlorophyll is a magnesium complex, all of you know. Hemoglobin is a iron complex. So whether we talk about hemoglobin, whether we talk about chlorophyll, whether we talk about vitamins like vitamin B12, numerous examples we can find where complex molecules are involved in the biosystem. On a later course of study, if you are dealing with the bioengineering, bioscience, biotechnology, biogenetic engineering and all, one of the major important complexing agent involved in the studies are EDTA. EDTA complexes are quite frequently involved in the studies regarding genetic science and genetic engineering. So biological field, great importance for complex molecules. And that is what the study concerned in the chapter, right? In fact, a theory regarding complex molecules, a detailed study about complex molecules was first done by Alfred Werner. He is called the father of coordination chemistry. Alfred Werner, called father of coordination chemistry, who was able to do a lot of simple experiments explaining the molecular systems in complex molecules with the simple experiments. And in fact, the first valid theory concerned to coordination compounds was given by Alfred Werner. Werner's coordination theory, right? Werner's coordination theory. He proposed the concept of primary valence and secondary valence. What is primary valence and secondary valence? Primary valence means oxidation number. Modern terminology, primary valence means oxidation number. oxidation number of a metal atom is called a primary valence, while secondary valence means coordination number, and these terms are primarily introduced by Alfred Werner. For example, if you take a complex molecule, say K4 FeCN 6 times, how to find the primary valence? That is the so-called ionizable valency. It is nothing but oxidation number of iron. How to find the oxidation number of iron? Very simple logic, everybody know. Potassium plus 1 into 4, it is plus 4. Iron, we want to find out X. Cyanide minus 1 into 6 minus 6 equal to 0. Therefore, X equal to plus 2, you get. It is plus 2 oxidation state, which is called a primary valence. Primary valence, the term used by Alfred Werner, is nothing but oxidation number. Clear? What is meant by secondary valence? Secondary valence means, primary valence means ionizable valence. Secondary valence means non-ionizable valence. That is satisfied inside here. Almost all of you may be memorizing. It is Fe surrounded with 6 cyanide. You see that? Cyanide 1, cyanide 2, 3, 4, 5, 6. This 6 bonding the cyanide makes surrounding the iron. The number of bond made around the central metal atom, that is called a coordination number. This is called a coordination number. Coordination number is in fact used by Werner as secondary valence. So primary valence means oxidation number. Oxidation number is called a primary valence, the term used by Alfred Werner. Coordination number is called secondary valence. That is the term actually introduced by Alfred Werner in his theory. Primary valence, secondary valence. He comments that every metal atom promote or exhibit a primary and a secondary valence. Primary valence means ionizable valence. Secondary valence means non-ionizable valence. Primary valence means oxidation number. Secondary valence means number of bond made surrounding the central atom. That is called a secondary valence. Okay. To understand this idea, he investigated a lot of simple experiment, conductometric experiment and electrolytic kind of experiment, precipitation reactions and all. Some of the examples are quoted in the textbook. You see a molecule taken, a compound taken with the different experimental conditions. For example, first of all, one experiment conducted, 1 mole of this complex, yellow colored complex taken. 1 mole of the yellow colored complex taken, which gave 3 mole AgCl precipitate when treated with silver nitrate. This complex treated with the excess of silver nitrate. This complex treated with the excess of silver nitrate, we were able to get 3 mole AgCl. Now the conclusion, what is the kind of formula we can assign? Very simple logic. What is the kind of formula we can assign? It is CO NH3 6 times Cl3. Now you can see this acts as a single entity. Coordination compound means complex compound represented in square bracket. It acts as a single entity. That is a non-ionizable system. And the ionization occurs over this region. This is the ionizing region, and you can find 3 chloride ions are available. So 3 chloride ions per mole of the complex interact with the Ag plus, and you are getting 3 mole AgCl precipitated. Ag plus interact with 3 mole of Cl minus, and you get 3 mole AgCl precipitated. That kind of experiment he conducted and was able to explain how the complex formula is coming. Now, the second case, a similar compound, 1 mole taken, purple colored compound, it gave 2 mole AgCl. What could be the formula of the complex? What could be the formula of the complex? COCl3, 5 ammonia. What could be the formula? CONH3, 5 times Cl2. Only 2 chlorine available outside the coordination entity. Outside that square bracket, there is 2 chlorine available. Out of the 3 chlorine, 1 comes in. Why? Because here we had 6 ammonia, here we have 5 ammonia, and 1 valency can be satisfied by chlorine. The secondary valency of a metal remain fixed. For example, cobalt will show coordination number 6, which is a constant. And that is what the observation explained by Alfred Werner. He says a metal show constant coordination number, constant secondary valency. Secondary valency found to be fixed. And what is the logic of his comment? Secondary valency fixed. You see, secondary valency 6, coordination number 6. Here you have 5. So out of 3 chlorine, 1 chlorine comes inside. So 5 ammonia and 1 chlorine. Now 6 is the secondary valency. And the result is, out of 3 chlorine, 2 chlorine available outside, which will precipitate, you get 2 mole AgCl. Is it clear? Now again, another example done on the 2 cases, 1 mole of this complex, green and violet. In fact, you can see both are having same formula. Same formula, different color means they are different compounds. So same formula, different compounds means that is isomerism. They are isomers. They are isomers. We are learning in the chapter geometrical isomerism can be exhibited by the given molecule, cis-trans isomerism. Right? Cis-trans isomerism. Cis can be violet in nature and trans can be green in nature. They are cis. We are going to discuss definitely on the later part of the chapter. Now, this when treated with the excess of AgNO3, you get 1 mole AgCl. What can be the formula? The formula can be CONH3 4 times. 4 ammonia there. So, we want 2 chlorine inside, 1 chlorine outside. So, only this chlorine can ionize and you get the AgCl precipitate. Right? So, the experiments concludes the nature of bonding that we get in the molecular system. So first one with the 6 ammonia, starting with the 6 ammonia. First case, the molecule was like this, CONH3 6 times Cl3, 3 chlorine outside. Second case, CONH3 5 times Cl2. Out of the 3 chlorine, 1 chlorine comes inside. So 2 chlorine outside. And the third one, CONH3 4 times Cl2, Cl. Only 1 chlorine outside. So the number of moles of AgCl precipitated can be observed from ionizing part. It is ionizing as 3 plus and chlorine minus 1 into 3. 3 chloride will give you 3 mole AgCl. 2 chloride will give you 2 mole AgCl. 1 chloride will give you 1 mole AgCl. So this will be 2 plus minus 1 into 2, 2 minus. This is plus 1 and minus 1 like this. Right? Now this can be termed as 1,3 type electrolyte. 1,3 type electrolyte. What is meant by 1,3 electrolyte? 1,3 electrolyte means 1 cation, 3 anion. That is 1,3 electrolyte. So what is this? 1 cation, 2 anion. What we call it as 1,2 electrolyte. So this is 1,3 type electrolyte. What is 1,3 type? 1 cation, 3 anion. What is 1,2 type electrolyte? 1 cation, 2 anion. Then what is this? It is 1,1 type electrolyte. 1 cation and 1 anion. 1,1 type electrolyte. So electrolytes may be categorized according to the number of ions we get. For example, if you take Al2SO4 thrice. Imagine it is ionizing. Imagine it is ionizing. What kind of electrolyte it is? It is 2 cation and 3 anion. It will be 2,3 type electrolyte. Like that. So number of cation anion obtained can be used to categorize what kind of electrolyte it is. And that experiment conducted by Alfred Werner to study about the nature of complex compounds. Even he has conducted electrical conductivity experiment. Electrical conductivity experiment is related to electrolytes. So he was studying in terms of electrolytes. What about if there is 3 ammonia? What about if there is 3 ammonia? What can be the condition? 3 ammonia if present. It can be CONH3 3 times Cl3. It is a non-electrolyte. It cannot ionize. There is no ionizing part. Here it ionizes here. You get 3 chloride and 1 complex. Here it ionizes here. You get 2 chloride, 1 complex. Here you ionizes here 1 chloride, 1 complex. Here it doesn't ionize. All the 3 chlorine inside cobalt. And imagine that is treated with silver nitrate, what will happen? Here you get 3 mole AgCl precipitation. Here you get 2 mole AgCl precipitation. Here you get 1 mole AgCl precipitation per mole of the compound. What about here? You don't get AgCl precipitation because the entire chlorine is inside the coordination entity. This is called a coordination entity, and in fact it is a non-ionizable valency. You look at that, ammonia number 1, ammonia number 2, ammonia number 3, chlorine, chlorine, chlorine. It available as a single entity, and you don't get the chlorine ionizing. Hope you understand. Suppose we are talking about the simple salt this. All of you know there is K plus and Cn minus. It will give you the test for cyanide. If you take this compound, there is Fe2 plus and Cn minus. So this will give you the test for cyanide. This will give you the test for cyanide. If you take this reaction mixture, there will be test for potassium. Solution contain potassium. There will be test for cyanide. There will be test for ferrous. Because there is K plus, you will get the test for potassium. There is cyanide, you will get the test for cyanide. There is Fe2 plus, you get the test for ferrous. But imagine they reacted and you get a complex. Imagine it is converted to complex. Now what are the tests you are going to get? Of course, you can get the test for potassium. You will get the test for potassium, but hardly you get any test for cyanide. You don't get a test for cyanide. Or the chances of getting a test for cyanide is very minimum because cyanide does not ionize. Now it is under non-ionizing condition. Hardly you get a test for cyanide, hardly you get a test for Fe2 plus. You don't get the test for Fe2 plus. You don't get the test for cyanide because it's available as a single entity, my dear children. This is available as a single entity. That is what the importance of coordination compounds. Hope you get the picture, right? So coordination compounds are formed by combination of simple and stable molecules. Simple and stable molecules. And there is a theory demonstrated or explained by Alfred Werner, that is Werner's coordination theory. Already we have discussed the main points in Werner's coordination theory. These are the important points in Werner's coordination theory. First one, metals show 2 types of linkages, primary and secondary valency. Already commented. Primary valency means oxidation number. Secondary valency means coordination number. Then primary valencies are ionizable. Secondary valencies are non-ionizable. Secondary valencies are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valency is equal to coordination number and is fixed for a metal. So when there is 4 ammonia inside, 2 chlorine also comes in order to make it 6. So 6 ammonia, no chlorine. 5 ammonia, 1 chlorine. 4 ammonia, 2 chlorine. 3 ammonia, 3 chlorine. So to make the secondary valency fixed 6, for example, the previous cases, you can see the number of chlorine introduced into the coordination entity from outside. So secondary valency fixed. That is what a main point established or explained by Werner's coordination theory. Ions groups bound by secondary linkage to the metal have characteristic spatial arrangement. There is a characteristic spatial arrangement. We call it as coordination polyhedra. Coordination polyhedra. There are mainly a few important coordination polyhedra. Coordination polyhedra, that is according to the geometry. Suppose coordination number equal to 4. Coordination number 4 means ML4 type. What is M? Central metal atom. What is L? The so-called ligand, atom or group bound to the central metal atom. Coordination number 4, there can be 2 important polyhedra. Number 1, it can be tetrahedral. All of you know the most famous hybridization of tetrahedral system is sp3. Most commonly encountered hybridization we learned from the main group elements. It is sp3 hybridization. There can be variations also. So normally tetrahedral means sp3 hybridization. It makes coordination number 4 and the system will be like this. This is the most commonly encountered complex system, tetrahedral complex. Right? Usually sp3 hybridization and coordination number 4, tetrahedral geometry. Okay. Now coordination number 4 can also be square planar system. What is square planar system? It undergo a hybridization, dsp2 hybridization, and it will be like this. Square planar system. So coordination number 4 can be either tetrahedral complex or square planar complex. Both are very commonly discussed complex molecules, all of you know. Right? Next is coordination number 6. Another important variety observed is coordination number 6. Coordination number 6 coming. It is octahedral system. Mainly we encounter either sp3d2 hybridization or d2sp3 hybridization. We are going to discuss in detail on the later part of the chapter. It will be like this octahedral system. This is octahedral system. ML6 type. ML6 type octahedral system. Most of the famous complex molecules are either tetrahedral geometry, square planar geometry, or octahedral geometry, which we are encountering in the chapter mainly. Of course, there are few others also commonly observed. That is coordination number 5 we come across. Coordination number 5, all of you remember, trigonal bipyramidal geometry. That is coordination number 5. It can be coordination number 5 of this kind. That is square pyramidal geometry. pyramidal geometry. This is trigonal bipyramidal geometry. So square pyramidal geometry, trigonal bipyramidal geometry, that is coordination number 5 systems, but less common compared to these categories. Most commonly encountered is tetrahedral, square planar and octahedral, and they are called coordination polyhedra. Coordination polyhedra. Okay, by simple analysis we can understand this is octahedral complex, this is again octahedral complex, 5 ammonia 1 chlorine, this is again octahedral complex, 4 ammonia 2 chlorine, right? This is tetrahedral complex. Many of the platinum complexes are square planar. Platinum complexes forming coordination number 4 mostly will be square planar complex. Of course, it is giving octahedral complex. And you can see the formula written here is conventionally according to old conventions. These formula written here is according to old conventions. Still in some of the textbooks you can find some of the questions, some of the textbooks you can find the old convention is still used. According to new convention, that formula to be written like this: CONH3 5 times Cl2 plus. You see, ammonia should be written first, then chlorine in the alphabetical order. When you write the formula of the complexes, first of all, the entire system should be in the square bracket, number 1. Number 2, metal should be written first. Metal should be written first. Number 3, ligands are listed in the alphabetical order. Ammonia A first, chlorine C next. So it should be in the alphabetical order. This is according to old conventions. Old conventions, the order of writing ligands was like anionic ligand first, neutral ligand next. Chlorine is an anionic ligand first. Ammonia is a neutral ligand next. That is old convention. According to modern IUPAC recommendation, the ligands should be written in the alphabetical order. Hope you understand. They should be written in the alphabetical order. Okay. So this is correct. What written here is, I am not commenting wrong. It is according to old convention. Okay. Now another important point. How do you compare this complex and this complex? CONH3 6 times, CONH3 5 times Cl. Hope you easily understand. This contain only one type of ligand, while this contain two types of ligands. This is called a homoleptic complex and this is called a heteroleptic complex. Homoleptic and heteroleptic. Homoleptic complex. This is called a heteroleptic complex. What is meant by homoleptic and heteroleptic? All of you may be aware of. Homoleptic means only one type of ligand. Heteroleptic means more than one type of ligand. Only ammonia come as ligand, homoleptic. Ammonia and chlorine coming, that is heteroleptic. So more than one type of ligand involved, that is heteroleptic. Only one type of ligand involved, that is homoleptic. Okay, right. There are few beautiful examples like this. There are some good examples like this, which also you must try writing the formula and all. For example, this complex, when treated with excess of silver nitrate, you get 2 mole AgCl precipitate. What will be the formula of the complex? Very simple. Very simple. It will be PdNH3 4 times Cl2. The 2 chlorine should be outside the coordination entity so that it can ionize and it can react with Ag plus and you get 2 mole AgCl precipitate like that. So when you say 2 mole AgCl you are getting, that means 2 mole chlorine should be outside the square bracket. 2 mole AgCl means these 2 chlorine should be outside. 0 AgCl, look at this, 0 AgCl, PtCl4 with the 2 HCl, and that will give you the very famous compound all of you may be aware of, H2PtCl6, chloroplatinic acid. Chloroplatinic acid, the entire chlorine inside the coordination sphere. Chloroplatinic acid, like that. Okay, so some example questions like this or in-text question like this, it's given representing some beautiful questions, particularly experimental evidences or experimental conditions elucidated by Werner is one of the prominent type of question we encounter in the exam papers. Some numerical type of questions, simple numerical type. Certain moles of the complex will give you certain moles of AgCl precipitate, then which is the formula correct? If the formula is given like this, how many moles of AgCl you get a precipitate? Like that, some simple numerical part regarding the stoichiometric aspect of complex compounds based on the simple experiment conducted by the father of coordination chemistry, the so-called father of coordination chemistry, Alfred Werner. Okay. A talk on double salt and complex salt. Complex salt already commented. What is meant by a double salt? What is meant by a double salt? You must go through. This is carnallite. Carnallite. There was a previous question. Molten carnallite upon electrolysis. What you get at cathode? What is obtained at cathode by the electrolysis of molten carnallite? That is an old question. The point is, without the knowledge of what is carnallite, you can't answer. Of course, after knowing carnallite also, you must know which will be coming at a cathode. At a cathode, you can get potassium and magnesium. Magnesium first, potassium next. Okay. So, at a cathode, it is potassium and magnesium deposited at the cathode, which you come to know as an answer if and only if you know what is carnallite, because the question carry only name. So you must go through such names in the NCERT. So that is carnallite. It is a double salt, more salt, ferrous ammonium sulfate, more salt. That's a double salt. Potash alum, that is a double salt. All these are double salts. Double salts. What is the importance of a double salt? A double salt is, you see, the formula seems to be complex. This is the formula of more salt. More salt formula seems to be complex. But that complexity only in writing the formula or in the solid state, not in the aqueous solution. When this more salt dissolve in water, you will get Fe2 plus ions in the solution. You will get SO4 2 minus ions in the solution. And you get ammonium ions in the solution. So you get 3 kind of ions in the solution. That's it. There is no complexity. There is no complex. Fe2 plus simple ion, ammonium simple ion, sulfate simple ion. So simple ions are obtained when the compound is dissolved in water. What about carnallite? You get K plus, Cl minus, Mg2 plus. What about potash alum? You get K plus, aluminium 3 plus and sulfate. So when all these compounds which are so called a double salt, of course their formula seem to be complex formula, but no problem. When it is dissolving in water, you get few simple ions. That is what the nature of double salts. Double salts are having complex formula but no complexity in aqueous solution. In aqueous solution, they dissolve and you get simple ions. Then what about complex compounds? Complex compounds, say for example K4FeCN6, when dissolved in water, you get 4K plus and FeCN6 4 minus. So this remain a complex. That part of the molecule remain a complex in the solid state as well as in aqueous solution. It is not ionizing as Fe2 plus and cyanide minus, already I have commented. It may not give you the test for ferrous. It may not give you the test for cyanide. Is it clear? So a complex compound means it retains the complexity even in the aqueous solution. A double salt means it may look complex, but there is no complexity when dissolved in water. It forms simple ion fragments. Is it clear? Fine. So that is an introduction about the coordination compounds, and there is now some terminologies related to coordination compounds. Some important terminology: coordination entity. This is called a coordination entity, that is put in square bracket. Something written in square bracket, that is called a coordination entity. This is coordination entity. This is coordination entity. So coordination entity will be put in square bracket. They will have a coordination polyhedra. Okay. Now, central atom or ion. Central atom or ion. Central atom means the central atom. Here the central atom is nickel. Here the central atom is cobalt. Here the central atom is iron. And they act as Lewis acids. Why central atom act as Lewis acids? Already commented. They accept a pair of electrons to make a bond, while ligands donate a pair of electrons to make a bond. Ligands act as Lewis bases and central atom act as Lewis acids. Okay? Yes. And the next important term is about ligands. About ligands. The term ligands came from the term ligare. Ligands means ligare. What is ligare? Ligare means binding. Ligare means binding. Ligands, ligare, binding. An atom or group of atoms that bind to the central atom is called ligands. An atom or group of atoms that bind to the central atom is called ligand. For example, CuNH3, it is making a bond. This is acting as a ligand. This is a ligand. And this is the central atom. Central atom accept a pair of electrons, act as Lewis acid. Ligand donate a pair of electrons, act as Lewis base. So this will act as Lewis base, this will act as Lewis acid. And what are the nature of the ligand? Ligand can be one atom. Ligand can be a group of atoms. Ligands can be very simple. Ligands can be as simple as fluoride ion. Ligands can be anion. Ligands can be neutral molecules, simple molecules like ammonia, water, etc. Ligands can be bigger molecules. Ligands can be macromolecules like proteins. So ligands may be neutral, simple units like Cl minus, anion, water molecule, neutral, ammonia, neutral. They are simple ligands which make only one binding, and they are called unidentate, which contain only single donor atom. In ammonia, nitrogen is the single donor atom and is called unidentate, monodentate. Is it clear? Monodentate. It can be two donor atom, like in case of ethane 1,2-diamine. This is ethane 1,2-diamine, abbreviated as EN. Ethane 1,2-diamine. That is a didentate system. Even oxalate, that is a didentate system. Let us analyze the nature of those two ligands. Didentate ligands, very popular one, EN and oxalato. EN means ethane 1,2-diamine. Ethane 1,2-diamine. This is the unit. CH2, NH2, NH2. This nitrogen carrying a lone pair of electron and this nitrogen carrying a lone pair of electron can make a bond with the central atom. So it is didentate. It is didentate. And even didentate, it makes a ring type arrangement. Don't you see that? It makes a ring type arrangement. It is making a bonding like this. NH2, CH2, CH2, NH2. It forms a pentagonal ring type arrangement. And that is known with a special name. I am sure all of you remember, chelating complex. This is called chelation or chelation. Such ligands are called chelating ligand. Such complexes are called chelating complex, metal chelate. Are they found to be extra stable or less stable? They are more stable. Usually, chelation causes extra stability. Of course, there are some abnormal situations when there is more chelation, make the molecule rigid. That's a different case. Normally, a chelating complex, due to this chelation effect, due to this that is called a macrocyclic stability. It's called a macrocyclic stability. It forms a ring type arrangement. So it's holding like this. It's holding like this. It forms a ring type complex formed, usually increases the stability of the complex. It is a didentate system. It is also forming a chelating complex. That is EN. It is abbreviated as EN. Normally we put within bracket. It is ethane 1,2-diamine, or common name is ethylene diamine. Ethylene diamine. Ethylene diamine, abbreviated EN. Alphabet will be E. Now there is oxalato, OX. Oxalato, abbreviated as OX. C2O4 2 minus. How is that forming oxalato? It is C double bond O minus, C double bond O minus, and that will make a linkage, 2 linkage at a time with the central metal atom. That also forms a ring type complex. So this is didentate. This is didentate. 2 density, 1 density here and 1 density here. There are 2 donor atoms which can make a donation at a time. Here also it is didentate. Here one binding, here one binding. Didentate. So one connectivity, unidentate. Suppose the metal atom connect with one donor atom at a time. It is unidentate. You see this? A metal atom connecting with Cn minus. It is unidentate. Or connecting with ammonia. Unidentate. This is unidentate. This is didentate. And the term used is dendricity. Dendricity. Number of donor atom making a bond at a time. Unidentate, 1 donor atom. Didentate, 2 donor atom. Tridentate, tetradentate, pentadentate, hexadentate, polydentate. Hope you get it. Look at the ligand available here. Look at this ligand. What is the density? N, CH2, CH2, NH2, the whole thrice. What is the density? What is the density of that ligand? It is N, CH2, CH2, NH2, whole thrice. What is the density? Please have a look at nitrogen connected to CH2, CH2, NH2. This is density number 1. Easily understandable, right? Look at this. CH2, CH2, NH2. Density number 2. Right? Look at this. CH2, CH2, NH2. Density number 3. So here it can make a connectivity. This nitrogen can make a connectivity with the central atom. This nitrogen can make a connectivity with the central atom. This nitrogen can make a connectivity with the central atom. What is the nature of the ligand? Tridentate. No, it is tetradentate. This nitrogen can also make a connectivity. Tetradentate. So unidentate, one binding. Didentate, two binding at a time. Like this. Tridentate. This is tetradentate. One of the most popular complexing agent in the chemistry in the chapter is EDTA. EDTA is very popular. EDTA is very popular. This is EDTA. This is EDTA. Ethylene diamine tetraacetate. EDTA. This is what the system. EDTA. EDTA is a very popular complexing agent. What is the density? What is the density? EDTA. How much is the density character? See, this can make a binding with the central atom. This can make a binding with the central atom. This can make a binding with the central atom. This can make a binding with the central atom. Not over. This nitrogen can make a binding with the central atom. This nitrogen can make a binding with the central atom. So one EDTA, the complex can go for octahedral geometry. One EDTA, the coordination can be 6. How 6 coordination? The central metal atom can go for a octahedral coordination. How it is possible? Look at this. One bonding over here. Just imagine this bonding over here. Just imagine this is binding here. This is binding here. This is binding here. And this is binding here. You look at that. One EDTA can make a binding, 6 binding at a time. Coordination entity will make hexa coordination. It is hexadentate. It is sometimes also called a flexidentate. Flexidentate means the density is flexible, not necessarily always 6. Not necessarily always 6. It is maximum 6. It can be 4 sometimes. That is flexidentate. EDTA, very popular one. And regarding EDTA, one very popular question came for IIT exam. It is asking for such a complex. For example, COEDTA minus. What is the coordination number? What is the coordination number? 6. 6 is the coordination number. COEDTA minus. Asking how many, you can try yourself. You can try yourself. How many oxygen, cobalt, nitrogen bond present in the complex? If you take cobalt EDTA complex forming octahedral complex, how many oxygen, cobalt, nitrogen bond present in EDTA complex mentioned? On old IIT question, you can try how much it is coming. So you have to be very careful understanding the connectivity and the molecular condition of the system, right? And that is the most important one regarding the nature of the ligand. Ligand can be simple molecules, ligand can be simple ions, it can be neutral molecules, simple molecules, or bigger molecules, or even it can be macromolecules like proteins. Macromolecules, bigger complex molecules. And there comes an important terminology, density. Density means number of donor atom making a bond at a time. Only one bond, unidentate, didentate, tridentate, tetradentate, polydentate, hexadentate, flexidentate. There is an important term, ambidentate. What is ambidentate? Ambidentate. Hope you remember ambidentate. If we are talking about a metal atom connected with a NO2 ligand, it can be connected like this, or it may be connected like this. Both are same, NO2. One case nitrogen is connecting, here oxygen is connecting. We call it as nitrito N. This we call it as nitrito O. Nitrito N, nitrogen getting connected. Nitrito O, oxygen getting connected. We have a ligand which can connect either like this or connect like this. That is called the ambidentate ligand. Ambidentate ligand. Ambidentate. Look at another example. A metal species getting connected to thiocyanate like this, or metal atom connected to NCS like this. Sulfur getting connected, we call it as thiocyanate S. This we call it as thiocyanate N. So nitrito N, nitrito O. Thiocyanate S, thiocyanate N, depending on who is getting binded to the central atom. This is called the ambidentate ligand. Ambidentate ligand. Okay. So that is about the nature of the ligand. Coordination number already we have commented, and please be very careful writing the coordination number in such examples. FeC2O4 thrice. Don't say coordination number 3, it is coordination number 6, because each oxalato is didentate. C2O4 oxalato is didentate. 1 will make 2 connectivity. So 3 will make 6 connectivity. Similarly here, coordination number is not 3, it is rather 6. So the ligands like En, which is didentate, ligands like OX, that is didentate, they will make 2 connectivity at a time. So you need to be very careful to giving the coordination number. Okay. That is regarding some terminology related to coordination compounds. This is a very important point. I think all of you are very much aware of. The coordination entity, coordination polyhedra, coordination number. Coordination number is decided. Coordination number is decided only by the number of sigma bonds. Pi bonds are not counted for the purpose. Pi bonds are not counted for the purpose. That we are learning in VSEPR theory itself. We are learning in VSEPR theory itself. Say for example, if we are talking with a molecule, of phosphorus oxychloride, say for example, phosphorus oxychloride, POCl3. What is the coordination system? The coordination system, all of you know, it is tetracoordinated. Phosphorus is surrounded by 1 oxygen, 3 chlorine. It is coordination number 4 basically. Right? How many bonds are there? How many bonds are there? You need to understand this multiple bond treated as if it is a single bond. Finding the coordination number, pi bond is not considered. Only sigma bond is considered. So what is the coordination? 1, 2, 3, 4. This contain a pi bond. Pi bond is not taken granted for deriving the coordination number. Coordination number is derived only basis of sigma bond. That we are learning even in the VSEPR theory. Coordination sphere. What is meant by coordination sphere? This is what called a coordination sphere. This is called a coordination sphere. This is called a coordination sphere, and this is called a counter ion. Potassium is called a counter ion. Right? Counter ion. For example, if you take a molecule, COEN 3 times Cl3, this is what called a coordination sphere, and this is called a counter ion. Counter ion. Counter ion can be anion, counter ion can be cation, and you know there are 4 types of complex molecules. There are 4 types of complex molecules. What are the 4 types of complex molecules? Type 1. Type 1. It can be a complex molecule of this kind. Type 1. As we were discussing earlier, CO, NH3, 6 times Cl3. This is type 1. We call it as cationic complex. You look at this. This is 3 plus and this is minus 1. The complex part is a cation. We call it as cationic complex. Cationic complex. Type 1. What about type 2? Type 2, naturally, anionic complex. K4, Fe, Cn, 6 times. You see, this is plus 1 into 4 plus 4. This will be 4 minus. This is anionic complex. So here, complex part is cation, cationic complex. Here, complex part is anion, called the anionic complex. Anionic complex. Is it clear? What about the third one? Third one, neutral complex. Pt, NH3, twice Cl2. There is no ion, non-ionic complex. So complex can be cationic complex. Complex can be anionic complex. Complex can be non-ionic complex. Neutral complex. Non-ionic complex. This is non-ionic. Non-ionic complex. Right? Now what about the fourth variety? I said 4. There is 1, 2, 3 and fourth one. This is fourth one. Cr NH3 6 times CO Cn 6 times. Here you can find this is one single molecule. This is 3 plus. This is 3 minus. Cation as well as anion is complex part. Both are complex. So this is cationic complex. This is anionic complex. This is non-ionic complex. And this is both type complex. This you can represent like this. Hope you understand. This you can represent like this. This you can represent like this. This you can represent like this. Hope you understand what the simple caricature I meant. That bigger one is a complex. So cationic complex, counter ion, anion. Anionic complex, counter ion, cation. Non-ionic complex, both cation, anion are complex. These are the 4 variety of complexes. Right? Coordination polyhedron already explained. Tetrahedral, square planar, trigonal, bipyramidal, square pyramidal. Most commonly encountered one, that also I told you. This is most commonly encountered. This is most commonly encountered. And where is octahedral complex? Yeah, there is octahedral complex. So octahedral, tetrahedral, square planar. These are the 3 most commonly encountered, particularly in the chapter. Most of the famous examples will come under either octahedral, tetrahedral or square planar. Of course, they are also coming. Then oxidation number, central atom, already discussed. Primary valency, oxidation number, already discussed. Homoleptic, heteroleptic, that is also discussed. What is meant by homoleptic? Only one type of ligand called homoleptic, 2 different type of ligands, that is called a heteroleptic complex. Homoleptic complex and a heteroleptic complex. That is about the basic terminology. And now what we are going to discuss is nomenclature, IUPAC nomenclature. regarding the naming and writing formula of the complex molecules. That is the point to be discussed.